In this video, we are going to talk about a special type of diodes. It's called the Zener Diode. And the Zener Diode was invented by a scientist called Clarence M. Zener by Bell Labs. And the Zener Diode is defined as a special type of semiconductor diodes that is designed to work as a regulator or to work in the breakdown region as a regulator. And the regulator means that if you have a changing voltage at the input of your circuit, if the input of your circuit is changing a little bit, there are fluctuations, the voltage is fluctuating, then the regulator is going to give you at the output of the circuit, it's going to give you a constant voltage. This is the meaning of regulation. So regulation means that if the input voltage of a certain circuit is fluctuating due to one reason or the other, there are many reasons that make the input voltage fluctuate, then the regulator is responsible to make this fluctuating input to be constant at the output, which is going to be connected, the output is going to be connected to your computer, your fridge, your appliance. So you need a constant voltage because fluctuating voltage may harm the appliance that you are connecting this voltage to. So the regulator, again, it helps removing the fluctuations from the input voltage and it will give you a constant voltage at the output. So the Zener diode is a special diode designed to work as a voltage regulator. What's the difference between the Zener diode and the regular diode? The Zener diode in the forward bias, it works as a regular diode. So if we operate the Zener diode in the forward bias region, if we try to push the current in the regular direction of it, in the direction of the arrow, then it will work as a regular diode, normal diode. So we can model it in the forward bias region, we can model it using one of the three models that we learned about the normal diode, which is the ideal diode, or we can model it using the constant voltage drop model or using the piecewise linear model. So in the forward direction, the Zener diode works exactly as the regular diode. So we can model it using ideal diode or ideal diode with a battery or ideal diode with a battery and a resist. The only difference between the Zener diode and the regular diode is that the regular diode, we assume that in the reverse bias region, it will be off all the time. Whatever inverse voltage that you put on it, the regular diode will be off. It doesn't break down, it will be just off. Okay, this is for the regular diode. For the Zener diode, this is not what happens. In the Zener diode, it is designed to work in the breakdown region. So the only difference between the regular diode and the Zener diode is that the Zener diode will have a breakdown region, and hence we have to model the breakdown region of the Zener diode. So here for the regular diode, we didn't model the breakdown region or the inverse bias. The inverse bias, the regular diode is off. For the Zener diode, no. We will not consider it is completely off in the reverse bias. There will be a breakdown region and we have to model. So let's talk first about the actual Zener diode in the breakdown region. We agreed that in the forward bias region, it will be similar to the normal diode. In the forward bias, it's very similar to the normal diode. In the reverse bias, there will be a very, very small saturation current until we increase the reverse bias voltage to a certain value, and starting from a certain point that we call negative VZK and negative IZK, the breakdown will start. So the starting point of the breakdown is defined as negative VZK and negative IZK. This is the voltage and the current at which the breakdown will start. Okay? And then when breakdown starts, the relation between the current and voltage, the current is going to increase in the reverse direction suddenly. and the relation between the current and the voltage will be approximately a linear relation, something like this, with a very high slope. And the slope here is very high and depends on the resistance of the diode, as we'll talk about later. So this is the point at which the breakdown will start. As we see, when we talk about breakdown, we are talking about all negative diode voltage and negative diode current, right? We have negative voltage. This is the regular the direction of the diode current, and this is the regular direction of the diode voltage. So now when we talk about breakdown, and this is the focus of our discussion now, we have all the diode voltages will be negative and all the diode currents will be positive. That's why here they define the reverse current and the reverse voltage of the diode, and they call them V Zener and I Zener. So they define I Zener to be in this direction, opposite to the regular diode current. And they define the V Zener to be in the opposite direction of the diode voltage. So basically, they define I Zener to be here negative I diode and V Zener to be negative V diode. Why is that? Because since we are going to work with all negative values of V diode and I diode, why don't we define I Zener and V Zener and work with positive values? It will be easier to work with positive values. So for example, we say that in order for breakdown to start, we need I Zener to be, it has to be greater than or equal of IZK. This is instead of dealing with negative values, instead of saying that for breakdown to happen, we need I diode to be less than or equal negative IZK, right? For breakdown to happen, I diode, it has to be less than or equal to negative IZK. So instead of using negative signs all the time and get confused with the negative signs, here we define I Zener to be equal to negative I diode and V Zener to be negative V diode, okay? And we deal with all positive values. So here, the first important piece of information is to say that in order for breakdown to happen, in order for the Zener diode to work in the breakdown region, this is the condition. So this is the condition to work in the breakdown or to operate in breakdown region. The Zener current, which is the reverse current of the diode, must be greater than the value that we define to be IZK. Usually this value is given in the data sheet, and if it is not given, then by default you consider it to be 0. So the value of IZK, the value of this current at which the breakdown starts, usually it is given. If it is not given, then you assume it is by default 0. Okay? And this is an important condition because we'll need it later to verify our assumption that the Zener diode is working in the breakdown region. This is how we verify it. Okay? And then we'll define some other important values on this curve. One of the values that we'll define is VZ0. VZ0 is, when you extend this line, we said that this part is approximately a linear relation. If we extend it until it intersects with the horizontal axis here, then this intersection point, we call it negative VZ node. Negative VZ node. So negative VZ node is the intersection between the horizontal axis and the extension of this line. This is negative VZ node. What's the importance of this? The importance of negative VZ node is that when we model the breakdown region, we are going to model it using just a straight horizontal line like this and then another line like this. the intersection point between these two lines is negative VZ node. So negative VZ node is the intersection between the horizontal axis and the extension of this linear relation. Another point is usually the data sheet of the Zener diode, it contains a test point. Test point means that they do a test for the Zener diode and they measure the voltage and the current in the breakdown region at a certain point. So they do a test and they say in the data sheet, they say that let's say our Zener diode will be working at this test current, negative I Zener test, at this test voltage, This is negative V Zener test. So they do a test for any Zener diode and they measure the current and the voltage in the middle of the breakdown region. They write these values in the data sheet and these values will be useful to identify the slope of the line and how the relation between the voltage and the current in this linear region, in the breakdown region, can be modeled. So far we defined some points. We defined negative IZK, negative VZK. This is the point at which the breakdown starts. We defined also negative VZO. This is the intersection between the extension of the linear relation with the horizontal axis. We defined the test point, okay, negative VZ test and negative IZ test. Now, in order to solve or design problems that contain Zener diodes, we need to model, similar to what we did with the regular diode. We modeled the forward bias region using 3 different models. Here we are going to model also the Zener diode. So the Zener diode can be modeled by a relation in the breakdown region, can be modeled by a relation that looks like this. So we can model it as here, reverse bias region. The current is completely zero. This is the reverse bias region. And then another linear relation that looks like this. This linear relation, it starts from the point negative VZO and then it goes down with a certain slope. Of course, since this is I diode, this is V diode, okay, we can model the relation now between the current and the voltage of the diode. Since we have a linear relation between them, we can model it using a resistance. We can model it using a resistance. But a resistance gives you a linear relation that passes through zero. A resistance would give you a linear relation here. Now the voltage is also shifted. There is a linear relation, but it is shifted by voltage negative VZO. So now, what do you think we should model the Zener diode with? If there is a linear relation but shifted in the voltage, then we can model it by a resistor and a battery. So the model that we'll use for the Zener diode in the breakdown region will be, if you assume that it is working in the breakdown region, then you will model it using a resistance that we will call RZ, and a battery VZO. And now the current I Zener will be going in this direction and V Zener will be the voltage here, and the relation between V Zener and I Zener would be V Zener equals VZO plus I Zener R Zener. Of course, if you look at the model, V Zener, the voltage across the diode, equals the voltage here plus the voltage here. The voltage here is VZO plus the voltage drop across the resistance, which is I Zener I Zener, R Zener. So this is an important relation. Why? Because we said that VZO is usually given in the data sheet, okay? And then if I give you the test point, if I tell you that we tested the Zener diode and we found that I Zener test and V Zener test, I gave you the values of I Zener test and V Zener test. Then you know that this test point, it lies on this line, right? You know that the point here, this test point, negative I Zener test and negative V Zener test, it lies on this line. So you can substitute on this line using I Zener test and V Zener test, okay, with a negative sign of course, because I Zener is negative I diode, okay, and I'm sorry, you have to substitute here with the positive sign, okay, because this is I Zener, and the I Zener is negative I diode. I diode is negative I Zener test, and I Zener is negative I diode, so it will be I Zener test. So I diode here at the test point equals negative I Zener test, and I Zener is negative I diode. So I Zener, you substitute it here by I Zener test. Same for V Zener. So if you substitute here V Zener test and I Zener test, you will be able to calculate the resistance. You can calculate the resistance R Zener. You will be able to calculate the resistance R Zener. Or I can give you the test point and R Zener, and from this equation you will be able to calculate VZO. So using one of them, one of RZ, and the test point, one of RZ and VZO, one of them, in addition to the test point, you can calculate the other value of R Zener and VZO. Okay? So this equation is also very important. You will use it to calculate either VZO or RZ from the test point. So I give you the test point, I will give you one of these two parameters and you calculate the other. Okay? So now, R Zener, let's remember, what's R Zener, Shabab? What's the ratio between R Zener and the slope of this line? This is important to know. The R Zener is the resistance, right? It represents the either the slope or 1 over the slope of this line. Depends on what? Depends on what is the vertical axis here. The vertical axis is the current. The horizontal axis is V. Then the Zener resistance, R Zener is 1 over the slope of this line. So the slope of this line equals 1 over R Zener. Why? Because the slope of this line is delta Y over delta X, right? Delta Y over delta X. Delta Y here is current. And delta X is voltage. So delta Y over delta X will be current over voltage, which is 1 over the resistance, right? So the slope of this line is 1 over R Zener. So again, if I give you the slope of this line, you flip it to, you can calculate R Zener. So you have to know all these definitions, all these tricks in order to be able to calculate the parameters of the Zener diode. Anyways, the model of the Zener diode, be careful, because the battery direction here, remember, it's always opposite to the current. So if the current flows in the Zener in this direction, then the battery will be looking opposite to the current. In the regular diode or in the forward bias, we used to, when the current used to go in the regular direction for the regular diode, I diode, we used to model the diode using a battery, and the battery direction again was opposite to the current. So this is VDO, and we used to put maybe a resistance here, RD. The current was going in this direction, and VDO was in this direction. So in the forward bias, the direction of the battery is opposite to I diode. Because in the forward bias, I diode flows in this direction, the direction of the battery is negative here, positive here. While here, in the breakdown, the current flows in this direction. Okay? Down. So the direction of the battery will be up. Okay, Shabab? So you have to be careful when you model the diode in the forward region, the direction of the battery will be different from the direction of the battery in the breakdown region. In the forward region again, I'll repeat it again, in the forward region, the direction of the battery will be negative towards the negative, positive towards the positive. But here, the direction of the battery is reversed, negative towards the positive and positive towards the negative. Remember always that the direction of the battery will be opposite to the current flowing. So if the current is flowing in the reverse direction, we are in the breakdown region, then the battery will be looking up, negative down, positive up. The battery will be opposite. Okay? Here in the forward direction, the current is flowing in this direction, then the battery will be trying to push the current opposite to the current flowing in the diode. So the direction of the battery is very important. If you flip it, you will mess everything up. Okay? So you have to be careful. So in this slide, in this video, we defined the Zener diode. We defined the model of the Zener diode in the breakdown region. This model is used only if you assume that it is working in the breakdown region. After you assume and you solve, you have to check, you have to verify that it is really working in the breakdown region using this condition that I Zener is greater than IZK, where IZK is the minimum current to make the Zener diode work in the breakdown region. If it is not given, then by default you can assume it to be 0. We defined the model RZ, it is 1 over the slope. The battery VZO is the point here, is the value of this point, okay? And the equation that relates the Zener voltage to the Zener current in this linear region. So these are important definitions, and we'll see you in the next video to see how to use these definitions.